Good morning from Berlin, from the UK, from Europe, but good afternoon in China. We are truly delighted to have you with us for today's seminar on ocean carbon sequestration and climate resilience. I am Chuanlun Zhang from Southern University of Science and Technology, and joining me as co-host is Dr. Yernar Sailybayev from the Caspian Environmental Consortium in Kazakhstan. It is unfortunate that one of the panel members, Dr. Jean-Pierre Gattuso, cannot join us for the panel discussion. To make up the time, I would like to show you a 13-minute presentation given by Professor Nianzhi Jiao, the chief scientist for Global Ones. This presentation was given at COP30, which is still going on. I think tomorrow will be the final day. He gave this presentation a few days ago, and it will be very timely to share with you for the latest development of Global Ones. So after Dr. Jiao's presentation recording, we'll start the formal seminar. All right, so this is what's happening at COP30 Brazil. Global Ones had this side event called Ocean Negative Carbon Emissions, the Ocean's Turn, delivering a science-based action plan for negative emission. This is a side event at COP30. The host organization is Global Ones. We have several guiding organizations and also participating organizations. Overall, the side event went extremely well, and Professor Nianzhi Jiao gave this keynote speech, and the title is "We Are in Action for Global Ones."
Hello, everyone. My name is Nianzhi Jiao. I'm the chief scientist of UN International Program called Global Ocean Negative Carbon Emissions, or WANS in short. We know climate change is the biggest environmental issue we are facing today. And global warming is mainly caused by anthropogenic CO2 emissions. And the term negative emission is the opposite word of emission. That means if the carbon flux of a negative emission equals that of emission, we're going to reach carbon neutral. For carbon neutralization, in addition to the land, we have the ocean. Actually, the ocean is the largest carbon reservoir on the Earth. The size of the ocean carbon reservoir is about 20 times that of the land and 50 times that of the atmosphere. So the ocean played a significant role in regulation of climate change in the history of the Earth. But the current ocean already has observed about 93% of total CO2 on the Earth. And if we do further negative carbon emission, we're going to take some risk. That's why science should go first. For carbon sequestration in the ocean, there are at least 4 known mechanisms, including solid pump, carbonless counter pump, biological carbon pump, and microbial carbon pump, which is responsible for RDOC carbon reservoir. RDOC means refractory dissolved organic carbon, which can stay in the water column for 5,000 years. So science commented the MCP as an invisible hand behind the vast carbon reservoir. The vast carbon reservoir referred to the DOC in the water column. And the size of DOC in the ocean is equivalent to the total inventory of CO2 in the atmosphere. So if there is an exchange between the two carbon reservoirs, there must be an impact on climate change. Like this case in the middle, you gotta have global cooling. And this case on the right, you gotta have a global warming. So in the past 10 years, we have published quite many papers in Science, Nature series, and PNAS. And MCT become a research direction followed by many researchers, even scientists from the terrestrial environments. And they proposed the soil MCP concept. So now we can see the MCP can be used as a solution to address some paradox, like why productive estuary areas are often sources rather than sinks of CO2. I would say that's because of the nutrients and environmental conditions, eutrophication. Another example, why productive coral reef systems are usually sources rather than sinks of CO2. And I would like to point it out that just because you miss the RDOC, which is produced by the MCP, if we include that part, the coral reef system could be sink rather than source of CO2. Another example, how to secure coastal blue carbon systems to be sinks rather than source of CO2. Because have the coastal area have emissions of nitrous oxide and methane, which can offset the carbon fixed by the coastal blue carbon, right? And if you add the RDOC, that means you close the budget. Then the coastal blue carbon systems must be sink rather than source of CO2. Another example is how to increase the carbon sink and avoid pollution in the agriculture area. So because we need the agriculture area for food, right? But it does have impacts on the environment. Then if we can do ocean nitrogen carbon emissions and remit the environment while increase the carbon sink, that would be a good thing, isn't it? Okay, so another example is how to turn the wastewater treatment plants from a source of CO2 to sink of CO2. This is a big challenge. And if you can make it, it will be a great contribution, right? So these examples show you the MCP is useful. Then let me show some practical approaches for carbon sequestration in the ocean. Number one, land and ocean integrated eco-engineering. So based on the carbon pumps I showed you, including the MCP, I can see if we can reduce the fertilization on the land on farming area, that could increase the carbon sink in the coastal water. This idea was proposed about 15 years ago. Then in the polluted area, hypoxic area, for example, we can also apply the pump, including the MCP, to enhance the carbon sink. Here, the MCP can work together with the CCP. And in that case, the CCP can be turned from a counter pump to be a positive one. So that is a good thing, right? And another example is artificial upgrading application in the seaweed farming area, like this. So this can bring up the new nutrients from the deep water to the surface water to enhance the fixation of carbon in the surface water. And the down weighting can compensating the oxygen, enhance the oxygen concentration in the deep water, and then to mitigate the hypoxic water situation. And while they can increase the carbon sink amount. And we can make good use of the facilities like this. This is so-called marine venting system. And we can also put all of the carbon pumps, BCP biological carbon pump, and carbonaceous control pump, and the solubility pump, as well as the microbial carbon pump together to make a BCA, a comprehensive approach for carbon sequestration. And that is actually a smart approach. Smart here means the initials of a specific, manageable, achievable, realistic, and transparent. So it's a potential-based practice. And as I mentioned, the wastewater treatment plants can also be used for carbon sequestration by harnessing microbial process as well as the enhancement of alkalinity in the water. And then you can release the treated wastewater into the river, is buried into the ocean, the cool water, and then it can split out and make a larger contribution of observed CO2 from the atmosphere. So this example, it can enhance the dissolution of olivine minerals in the wastewater by 18 times than the normal water. Okay, so this way we can develop the protocols for even international standards towards the SDGs. And actually, we have already got approved by the ISO, the International Standardization Organization, to establish a working group on ocean negative carbon emission and carbon neutralization. So this is good platform for people here who are interested in to propose your techniques to develop into international standards. Now, Global Ones has been joined by 17 teams from 33 countries. An example of collaborations with the American Academy of Microbiology, we have formed a strategic working group on microbes and climate change. And we have published a paper titled Microbes Without Border, and which has been published in 6 journals simultaneously. Collaborations with the European scientists, we have published the assessment report on ocean-based solutions to climate mitigation. Collaborations with the TWICE, the World Academy of Sciences for Developing Countries. We have formed a standing committee for climate change with 9 members from different countries, including me. And Global Ones have been very active in academic activities like COPs and the Ocean Decade conferences, as well as a World Laureate Forum and the Davos Forum, EFG, Global Trading Service Summit, Global Dialogue of Civilizations, and STI by the UNDESA, Science, Technology, and Innovation Forum, where I propose the Global Ones approaches to the global audience and got very positive responses. And we scientists reached to a consensus, and we get a policy brief published, which is about water quality and carbon sequestration in the aquatic environments. Of course, we have science education and popularization activities. Like this one, we created a new course titled Habitable Earth, which is now being translated by AI into 30 languages and will be made available on the internet for all peoples, all audiences all over the world. And here are some cases of our open science conference. Finally, I would like to make a call. Science is a global language. Together, we're going to make a difference. Thank you.
I hope this CAP 30 presentation will enrich today's seminar. Now, it is with the great honor to introduce today's keynote speaker and panel discussion member. So first, Professor David Ho, who is an oceanography professor at the University of Hawaii in Manoa. Professor Ho is focusing on marine carbon removal and climate change research. He has made significant contributions to understanding biogeochemical cycles, ocean atmosphere interactions, and the role of marine systems in climate regulation. Professor Ho earned his Ph.D. in Earth and Environmental Sciences from Columbia University in 2001 and has authored over 80 publications in leading journals, including Science, Nature, Nature Geoscience, and GRL. By the way, David, I met a few of your colleagues from Columbia University, so we can, share this information later on. Okay, so following his presentation, we'll be joined by Dr. Christopher Pearce. How do I say your last name, Chris?
Yep, that's right.
Okay. All right. So Dr. Pearce is an oceanography scientist at the National Oceanography Center, UK. His research centers on the assessment and evaluation of climate change mitigation strategies, including marine carbon dioxide removal, MCDR popularly, and enhanced rock weathering, ERW techniques. Got all the good names. He leads the multidisciplinary CO2 CDR project. That's SEAO2, very creative. This project develops governance frameworks for MCDR and assesses potential implementation pathways. He also contributes to quantifying the effectiveness of CDR via basalt weathering in agriculture environments. That sounds like a very interesting idea. For more information on their research and accomplishments, you can visit the Global One's website at www.global-ones.org. All right, so without further ado, let's extend a warm welcome to Dr. Ho and Dr. Pearce. Okay, so David, you can now start your 30-minute presentation.
So thanks for having me, and I know it's very early for some of you, so thanks for getting up. So I'll dive right into it. So these are your take-home messages, right? So MCDR, marine carbon dioxide removal, it's different than terrestrial-based CDR because it's at least a two-step process. One, you do some sort of intervention to the ocean, but then you have to wait for the ocean the new ocean state to equilibrate with the atmosphere in order for any CDR to happen. And MRV for MCDR, it's really challenging because of a number of issues. The signal to noise is very small. There's a lot of natural variability. Carbonate chemistry is complicated. Ocean mixing and circulation makes it so that it's a large scale process. So because of these reasons, actually, direct observations is not possible. And also, even if, these things didn't exist, it's still not possible to use direct observations for MRV because you need to observe a counterfactual, right? What would have happened if you hadn't done this deployment? And that's just something that can't happen by definition. So we need to use numerical models, but the models that we have now are not currently ready for this. And they really need a lot of work, and I'll talk a bit about that. So as I said before, MCDR is a two-step process, right? So on the bottom axis here is time, and then let's say PCO2 on the y-axis. So step one, you do something to reduce surface ocean partial pressure of CO2, right? But that's not yet CDR because in step two, in one scenario, that water subducts and it's not in contact with the atmosphere anymore. And you've done nothing to the atmosphere, right? Because it doesn't take up CO2. And in step two, let's say the water stays at the surface and you have equilibration over time and you actually do something about atmospheric CO2 and climate. So it's really important to figure out what happens to your water after you do some sort of intervention. And we use this term MRV, which comes from the carbon market. It stands for monitoring, reporting, and verification. But really, when we talk about it as oceanographers, we really just mean the M part, right? Because we're not reporting the result to a third party who then verifies the results, right? So we basically use MRV as a shorthand for monitoring. Okay. And there are two requirements for MRV. One is additionality. We want to know how much extra carbon did the ocean take up relative to some counterfactual where, the intervention didn't happen. And two, we want to know how long the extra CO2 is kept out of the atmosphere after removal. Right? And then there's this debate about whether environmental impact is part of MRV. So some people are now saying CMRV for carbon MRV versus EMRV for environmental MRV. But I think for the purposes of this discussion and maybe just in general, you might view any kind of ecosystem harm as what I call a gating criteria, which means that if intervention is going to do some harm, then you don't do it, right? So that's one way to keep things simple and keep MRV for carbon uptake quantification. So there are different methods. You just heard in the previous presentation about some ideas about how you reduce atmospheric CO2. And people have proposed a whole bunch of different methods and also proposed different ways of categorizing those methods. And you can see in this diagram on the right, there's this sort of Venn diagram that sort of distinguishes all these different ways that people have characterized the methods. And for the purpose of this presentation, I would characterize them as abiotic methods, not biological, and then biotic methods, right? So you have methods like ocean alkalinity enhancement, direct ocean removal, which are the abiotic methods. So they fit into this circle on this side. And then the biotic methods, which include growing macroalgae, kelp, or fertilizing the ocean or artificial upwelling, and then also considered is blue carbon restoration, so mangroves, salt marshes, and seagrass. Okay. And the challenges for abiotic versus biotic MCDR are very different when it comes to MRV, right? So let's just run through this the sort of simplified version of what needs to be done. So for an abiotic intervention, you want to know, well, did the intervention happen, right? Did you add the rocks to the ocean, or how much of the rocks did you add, or how much sodium hydroxide did you add? And then for OAE, for direct ocean removal, you want to know, well, how much CO2 did you remove from the ocean? And then you want to know the ocean response. Like how much did the alkalinity increase in the water? Or how much did the dissolved inorganic carbon decrease? But then you want to know how much did you change the PCO2 in the water? Okay, so none of that is CDR yet, right? The third step is then you want to know how much additional carbon did the ocean take up? I mean, embedded in this is a lot of work, right? But already in these first two steps, there's a lot of things that we need to monitor and measure. Okay. And for biotic, okay, you have something similar, right? You want to know, did the intervention happen? Did we add the iron to the ocean? How much iron did we add? Or how much kelp did we grow? And then you want to know the ocean response. Did you increase productivity? Did you increase the chlorophyll in case of fertilization? And then ultimately, did you decrease the surface ocean PCO2? Now, before we get to how much additional CO2 was removed, you need to know a whole bunch of other stuff. Because you are producing organic matter, you want to know, well, how much of it makes it to the seafloor? How much kelp did you harvest? And most likely, most of it will not make it to the seafloor. So at what ocean depth did it remineralize? And then if it does, for the 1% that makes it to the seafloor, how much stays there? And what about the dissolved organic carbon you're shedding? And I just want to point out this is a very difficult process, right? Like to find something in the ocean is very hard. Even if you have some general idea about where it went in. Right? Just remember the Malaysian Airlines plane. Like we couldn't find it. We know it's in the ocean somewhere. We couldn't find it. Um, and these particles are way smaller than an airplane, right? And then we also want to know about the side effects. If you're using nutrients, the macronutrients to grow your phytoplankton or kelp, then you're taking it away from something else that might have grown in its place. So we want to know about the potential nutrient robbing that happens. And then in certain cases, you're going to produce other greenhouse gases like N2O, and you got to account for that. And then you can get to, well, okay, what is your counterfactual? So I would say the biotic MRV is quite difficult. But I will, for the rest of this talk, mainly focus on, how do we quantify this additional CO2 that's removed? But let me say a few more things about how difficult it is to do MRV for the biological intervention. So there's an ocean time series in the Atlantic called BATS, the Bermuda Atlantic Time Series. And there, over many decades, they've been measuring community productivity at the surface, and then they've been looking at particle fluxes. And even at the site where they've spent tens of millions of dollars on the science, they can't reconcile the the difference that they get between the productivity that they measure at the surface and the export flux that they get at depth within a factor of 3, right? I mean, there's a big difference between these numbers. And this is essentially what you have to do for MRV for biotic MCDR, right? So I would say this seems pretty impossible. Okay. Now, in general, why is MRV for MCDR so difficult? Well, first, the scales are huge. Like the ocean is very big, and this signal is going to spread to an entire ocean basin. And the ocean already takes up a lot of CO2, right? Like the latest number from the global carbon budget is that it takes up 12 billion tons of CO2 every year. So we're talking about a small signal. Every deployment is going to be tiny compared to billions of tons of CO2, right? And then you need the counterfactual. You need to know, well, what would have happened if you didn't do anything? And then there are certainly processes that we don't understand that we're not accounting for. So just as an example of how large of a scale we're talking about, this is a modeling study that we did where in the coastal areas we uh, basically you can consider the top one direct ocean removal and the bottom one is cultivating kelp. And what happens is this is results over 5 years. And everything was happening at the coast, but you see the resulting CDR happens all over the ocean, right? And there's just no way that you can cover that with measurements, if even if you wanted to. And and the reason that the signal travels so far is just because that equilibration between the atmosphere and the ocean takes a long time. It's not instantaneous. If it was instantaneous, it might just stay along the coast. And then this is another numerical model simulation of air-sea CO2 fluxes. And you can see, well, each of these is a day. So it's going by very quickly. But there's a lot of variability in where the ocean takes up CO2, where it gives off CO2. And and on top of that, you're trying to detect a very small signal. If you make any sort of deployment here, it would be very hard to see on top of this very large noise. Right? And let's say you come from a country that's very ambitious. You think, oh, we'll just deploy tens of millions of sensors in the ocean to measure any of these changes. Well, so one thing you want to detect, let's say for ocean alkalinity enhancement, is the change in alkalinity. Um, but right now we only have sensors for pH and PCO2, and not very good ones either. And if you look at this plot on the right, if you focus on the bars that are very big, so what this shows is the error in alkalinity that you would calculate by measuring pH and PCO2 using different dissociation constants. But no matter which one you use, you're going to get a huge error in the calculated alkalinity from these sensors. So it's a very bad way to do things. Sensors and plus, I don't think we're ever going to deploy millions of these sensors in the ocean. It would just be way too expensive, right? Um, and then you might say, oh, well, let's go out and measure DIC, dissolved inorganic carbon. But this paper from Rick Quanikoff and colleagues showed that over a decade, they do these repeat transects in the ocean where they measure carbonate chemistry, and one of the parameters they measure is DIC. So over a decade, the ocean has taken up at least 100 gigatons of CO2, right? But these really good carbon chemists go out there, including Dick Feely, Taro Takahashi, and others. They can't see this ocean uptake of 100 gigatons of CO2 based on measuring DIC, right? It's a really hard problem, even if you have the best measurements available to you. So we 2 years ago we published this best practice guide for ocean alkalinity enhancement research, and I led the chapter on MRV, and our suggestions there was we need to determine which observations are needed, right? And then have fit for purpose models that are calibrated and evaluated with observations. And the observations that we suggested include like, okay, you need to know something about the physics, You need some tracers to see where the water is going, get a sense of the gas exchange, and just basic like temperature, salinity, carbonate chemistry, etc. And so our suggestion then was, okay, these models aren't ready, but we need a real program to make these models ready as credible tools for MRV. But then eventually, because high performance computing is expensive, but it also, of course, uses a lot of power, electricity, and probably um, it would be a source of CO2. We want to reduce the cost of that, both in terms of carbon, energy, and money. You want to use some sort of, machine learning approach to generalize these results. Right? So that was our recommendation. So let's look at the different scales that we're talking about, right? So the deployments are on very small scales if you're talking about putting chemicals in the water, and then maybe on slightly larger scales if we're talking about growing macroalgae or iron fertilization. But on these scales, you need some sort of mixing zone model, like what people use for permitting discharges in sewage treatment plants, right? But then um, we need regional models to look at the signal on these sort of local to regional scales. But then to get the uh, additional carbon uptake, you really want regional models to global models, right? So there's a scale of different models that we need. And we need data, right, to evaluate those models. So these are drone images from a dye experiment that we just did in a fjord in Iceland. So this white dot here is a boat that's a few meters long. So just to give you a sense of the scale, and this is a oil transfer pier. And so every image is 10 minutes. So you see this dye experiment that we did to get a sense of how fast the dilution is. So this is in preparation for a sodium hydroxide release, which is a base. So that's your source of alkalinity. And you would want a model to be able to simulate this spreading of the dye and just get it right, right? Otherwise, you're going to get completely wrong results, right? So this is on a very small scale, right? Really, really fast over a period of minutes. You want to be able to simulate, depending on the tides and currents, what happens here. But then you want to know on a sort of larger scale what happens. So this is an experiment that I led in the Southern Ocean quite a long time ago in 2008. But we put sulfur hexafluoride in the water and tracked it over weeks. And so this goes over tens of kilometers, right? But you want a model to be able to reproduce these results, but also um, having tracer release experiments like this allows you to do a Lagrangian study, right? You can see what happens actually inside the tracer patch. And this is what was done in these iron fertilization experiments that have been done all over the world. So this is one that was published by Ken Cole about it's called IronX, the experiment. It happened in the Pacific where they put iron in and they put SF6 along with it. So this going through here is days, so up to day 17. And over time, you see the decrease in the iron. So the SF6 allow them to track the patch. And then you see the increase in chlorophyll because you're stimulating a bloom. And then the change in surface ocean PCO2 that happens, right? So experiments like this are really important for you to see that something is happening, but then to provide data for models to try to simulate so that you can see if you can trust these models. Okay. And one thing that's important to note is that a lot of these deployments will be from the coast. because that's where people are, that's where infrastructure is, that's where energy is, and that's where your material um, is located. And in coastal areas, air-sea gas exchange is very different than the open ocean. And air-sea gas exchange is what controls the flux of CO2 between the atmosphere and the ocean, right? So here are three experiments that I'm showing you from my group where if you take this, there's a parameterization that I produce for the open ocean, Ho et al. And so that's what you might use if you're looking at an experiment in the open ocean. But then if you look at the results, these points here and these red and blue points down here and these black points here, all of these points from these coastal and nearshore areas are very different than what you find in the open ocean. And people are still in their modeling using the open ocean parameterizations, which would give you a very different result, right? It would imply that the equilibration is happening a lot faster than is actually happening. And depending on the residence time of your water in these coastal areas, it would matter a lot for the results that you would get. And then this is from a recently published MRV document from the European Marine Board that shows that the carbonate system observations that we have in the global ocean is actually decreasing. So on top is DIC, and on the bottom, well, is leveling out and decreasing a bit is the PCO2 measurements. And these are really important measurements for us to know the background state of the ocean. So if we stop doing this, we're not going to know, the sort of counterfactual case of what is happening in the ocean, right? So I think that, our energy here is focused on MCDR and MRV for MCDR, but just maintaining the backbone infrastructure that we have is super important for us to understand what's happening to the ocean. Now, startups are currently doing these small scale deployments and claiming credits, in order to keep going. And the way they're doing it is with regional models. They may not be fit for purpose, but they will give you a result. And they're currently using this to say, okay, this is how much CO2 how much additional CO2 we're taking up. But I would say that this still needs a lot of work, right, in order to be trustworthy. Okay. And then we had done this study where we divided up the ocean into these polygons and then injected alkalinity into each polygon and saw what happened. And then this was the result. And so we did it in 4 different seasons and then saw what happened after 1 year, 2 years, 4 years, 8 years, and 15 years. And the color bar indicates the efficiency. So in red is very efficient, in purple is not efficient. So if we just look at January, you see after 15 years, let's say, you see the places that are good for this and the places like the North Atlantic that are bad for this. And I would pay attention to the coastal areas because that's where I think deployments are going to happen. So studies like this might give you a general guide as to what area of the ocean might be good for this kind of deployment. And then maybe, if we produce very good regional models, we can reproduce this study with regional models that are trustworthy, and then be able to have these systems where somebody can just click in one place in the ocean and really see the uptake curve over time, and they don't have to run models. But this is a dream for decades from now, right? There's one thing I want to say, which is, how well can we believe these models? So this is a figure from the recently released global carbon budget that came out last week, right? So it's very fresh. And one thing that, if you pay close attention, you might notice is that okay, so you have these sort of purple lines, these thin purple lines. These are the models runs, right? And this is time, this is the ocean carbon sink. And then in this green color are the database products. So this is using PCO2 and the gas transfer velocity to get a sense of the ocean carbon sink. And then the black line is sort of the mean between the two. And the thick purple line and the thick green line are the averages of the data and the model. So you might ask yourself, if you're averaging the data and the model, why is the black line not between the two lines, right? And this is the first time this has happened. And when I asked Pierre Friedlichstein, who's the lead on this, he said, "You're the first person. I'm the first person to notice that the black line doesn't sit between the two." Right? And the reason for that is because they made an adjustment to both the model and the data, but they only did it to the average, right? They published this Nature paper where they said we increased the model estimates by 10%, and we increased the FCO2 products, that's the data products, by 0.18 gigatons of carbon per year. But they only did it to the thick lines, and they didn't do it to the individual runs. And so that shifted everything. And that's why the black line sits in this funny place. But the fact that from one year to the next, they all of a sudden corrected the ocean carbon sink by 180 million tons, right? Get that number in your head, 180 million tons from one year to the next. I mean, if MCDR deployments can take up 180 million tons, we all be celebrating. But there's this uncertainty that is so huge that, even the best scientists in the world from one year to the next says, oh no, we got it wrong. It's something different. I mean, this is really important to keep in mind, right? Our ability right now to say something accurately about what the ocean is doing, it's not that great, right? Okay, so there are different sources of uncertainty that contribute to this. There are uncertainties that arise because we are undersampling something in the ocean. But then there are uncertainties that arise because we're not sampling the thing that we should be sampling. Um, and then there are uncertainties that arise because we don't understand something in the ocean, right? And then there's like chaotic dynamics that just we can't get rid of. So there are some things that we can actually solve in these models and in our conceptual understanding of what's happening in the ocean that would make things better. So just I'm almost done, but I want to say, because MRV has to be done with a model, what makes a model reliable? And I think this is an important question. We know that models are full of bugs, full of errors. But the question is whether they affect the results that we care about. So, ultimately, I think we want a model that can reproduce, let's say, the tracer results that I showed you, right? I mean, that's important because that gets the physics right. Um, that can predict environmental variables that we can easily measure. That's important. And have reliable, equations and parameterizations like the gas exchange parameterization that I talked about before. If we know that something should be a certain way, it should be in the model, right? And it should perform well against previous observations. You should be able to model, real world observations. And you can capture the relationship between things that are predictable, like nutrients and carbonate chemistry, and so on. And here's the important thing, right? The reason that there are so many models run for this global carbon budget is because no single model outperforms the multi-model mean in anything that we do. Down here it's CMIP, right? Like IPCC runs. It's the same thing. You take a mean of of many model runs, and then you have a reliable result. And also running multiple models gives you an idea of the uncertainty in your estimates. But the question is, do you run an ensemble of the same models with different parameterizations, or you run a bunch of different models, right? That's a conversation to be had. But okay, so this is my conclusion. So what I think is needed for MRV of MCDR. So I hope from this you get that. My feeling is that we're not ready to do this, right? So we need tracer studies to determine gas exchange, residence time, circulation, mixing, get the physics right, right? We need to do trial deployments of these techniques and then make measurements to see what happens. Do we have an understanding of these processes at all? And measure things that are relevant, the carbonate chemistry, trace metals if you're putting rocks in the water, nutrients if you're putting rocks in the water, or if you're trying to do one of the biological techniques, you want to know about particles that you generate from changing carbonate chemistry, right? You might have secondary precipitation, so particles in turbidity, etc. I think it's really important that we have these global observations of carbonate chemistry, nutrient distributions, things that we can sense remotely from space, ocean color, temperature, salinity, because we need to make sure that we understand the background state of the ocean and to evaluate these global models. Now, in terms of models, we need high resolution regional models that are calibrated and evaluated with the fit for purpose field data that we generate, and then global models of varying complexity to figure out the best location for deployments, but then to figure out also CDR efficiencies and side effects and so on. But eventually, I think, once we get all the modeling tools to the point where they can accurately predict these results, we need to get away from these models in order to not have to run them every single time, because it's very cumbersome. And with that, I am happy to take questions with Chris.
Okay. Thank you so much, David, for an excellent presentation. It is really insightful, authoritative, and detail-oriented. It's a great lesson. I'm learning how to be careful when you say anything. Hey, I'm very successful with my MRV. A lot of details are involved. Now let's move on to the panel discussion. As David invited Chris, Dr. Pearce from the National Oceanography Center, the UK. So, Chris, as David invited, what is your opinion on the confidence that we might have to perform MRV? And since the people are trying to use MRV as a way to enable carbon credits to be sold on the voluntary market, what's your advice? What's your comment on all this?
Thank you very much. It's a pleasure to be able to join you, and thanks, David, for a really fantastic talk. That was really, really insightful, and I echo and agree with pretty much everything you just said. I would say I'm a little bit more positive on our ability to conduct the in situ measurements, not least because colleagues at the NOC are developing and have released in situ alkalinity sensors. So we are continually advancing our ability to make those measurements, and whilst perhaps not quite at the standard of lab-based measurements, I think we are certainly getting there. Nevertheless, you're absolutely correct that there is this inherent trade-off between those in situ observations and the reliance on models. And for me, the key question there is you're right about this, it's the uncertainties, but it's our confidence in our ability to do MRV. How do we, what are we trying to achieve? Who's setting that barrier of what we need to reach? And this kind of then relates to this voluntary carbon market question, in that to date, we have to acknowledge that most developments of marine CDR, certainly the field trials, which are essential for advancing our understanding of our ability to make those measurements, have been led by commercial entities. We need to do more independent research on them. We need to have independent funding to drive our knowledge forwards. But commercial entities who have been driving them, and David gave some examples, are relying on selling carbon credits to facilitate that. So there needs to kind of be there's this tensioning between enabling them to proceed and drive forward and enhance our understanding, and enabling them to actually sell credits that are meaningful and are realistic representations. And David made the point that our models are not fit for purpose. That I would say is recognised. There are underselling of these credits at this point in time, made on assumptions and sort of cutting down to say, well, we're doing some good and something's going to come out. I think perhaps that's obviously not going to be sustainable in the long term. We have to say, right, we need to make it more fit for purpose. So we have to say, actually, what you're doing may not be drawing down anywhere near the amount you're saying because of this mixing uncertainties. But we essentially have to be starting somewhere. And to that end, I think we have the ability to make these measurements in situ, but we have to have confidence and an ability to say where we're handing off. And that can only come by, as Dave said, by doing more in situ field trials, testing our techniques. I do think we will get there. We certainly have the ability to measure, as Dave said, our actions and the perturbations in a near field on the marine system. So we can kind of look at what we're doing. It's just that correlation to the CDR, that actual CO2 drawdown, which is going to be inherently reliant on models. And that's where we need to get our confidence in what we're actually saying is done as the carbon benefit. And that will differ from a carbon market perspective to perhaps a compliance market where you're looking more at, we're doing some greater to good. And ultimately, there we have to acknowledge that marine CDR is only one part of the parcel, and with all the other CDR options on the table.
Okay, Chris, I want to tell you at COP30, I met your colleague, Professor Sean Fitzgerald, the director at the Center for Climate Repair, University of Cambridge. He spoke highly of your research in teaming up with them. Can you briefly introduce us your program in the UK, and how far are you from really, getting somewhere, as David indicated, to be ready to really say something about the effectiveness of MSDR?
Yeah, I've been delighted to watch from afar the progress being made at COP. I look forward to kind of hearing what the outcomes are. Obviously, it's great this year that it's been the first time there's been a CDR pavilion held at COP30. So, I do hope that continues, as well as discussions at the Ocean Pavilion and other places. In terms of the work being done through CO2 CDR, this is very much an interdisciplinary approach, trying to bring together different actors in this space. Specifically focusing on MRV. We have colleagues at the NOC who are about to go and deploy our alkalinity sensors with Dalhousie and Planetary at the field trial that David highlighted. So we are about to look at our ability to conduct those in situ sensors. And we're also currently on a separate project working with David and the Carbon Sea funded project in Iceland, looking again at our ability to use autonomous platforms for conducting these sensors. So actually, I think it was that tiny little white dot floating around above David's boat in the time-lapse images he showed would have been a USV platform. And I think all these field trials, all these works in the continual deployment of sensors will give us enhanced knowledge of what we can measure and what we can currently do. And I think we have to look in near term and our ability to make those measurements if we're going to have any hope of upscaling these. We have the technologies in the pipeline, we have the ability to do these measurements. It's just kind of giving ourselves that confidence. The next question, of course, is, well, how do we use them to upscale and what we're going to do at bigger and bigger variations? And that's kind of where you then hand over to modeling. And going back to the CO2 CDR project, delighted to have Andreas Schlees and Sandy Avratin at Yernar currently looking at this integration, as well as John Taylor at the University of Cambridge, a colleague of Sean's, doing some work around kelp and carbon uptake within macroalgae fields. So we're certainly looking at this integration of measurements, and there's a wider parameters that need to be used in this setting. So yeah, hopefully we've got a year and a half left to go on that project. So hopefully more results coming in the near future.
Okay, thanks for the introduction on your project. I have a couple of questions for David. The first one is you separated MCDR between abiological and biological. for the biological MCDR, you did bring up the organic matter being an important component of the equation. I'd like to hear your comments about the RDOC being in the equation. As you watched Ninja's presentation about the RDOC serving as a reservoir of storing CO2 in a water column. Would that make, what kind of difference would it make if you consider RDOC in the biological MCDR?
Yeah, I think so. The difference between the the chemical methods and the methods that rely on biology is that with the chemistry, what you're doing is you're storing the carbon
Hmm.
as bicarbonate, basically, right? Because
Right.
90% of the dissolved inorganic carbon in the ocean is bicarbonates, and that has a long lifetime in the ocean. Like no matter where you put it, you're
Hmm.
looking at tens of thousands of years. Whereas with biology, you're relying on it not one not being CO2, but two not being near the surface of the ocean where it could be somehow turned back into CO2 and exchanged with the atmosphere. So I think the problem is that you then really need to make sure that whatever you're producing gets to a level of the ocean where it doesn't come back for hundreds of years.
Hmm.
And and it's the issue there is that it's really hard to check
Mm.
that this is happening, right? So one thing about it's like geologic storage of CO2 on land. You have
Hmm.
to keep monitoring it or in under the seabed. You have to keep an eye on it and make sure it doesn't come back out. And
Mm.
somebody has to be responsible for that.
Mm.
And that just adds another step to MRV, I think. And
Right.
yeah.
Okay. Great. Thanks for your insight on RDOC. My next question is about your perspective. You seem to be very cautious about the effectiveness of MCDR for really having CO2 stay in the ocean. And based on my understanding, we are not ready really for say something absolute about MCDR. So what's your timeline? At what stage we will be ready to say, hey, MCDR is effective
Yeah,
based on your own research and also as a global collective effort?
so I think I don't know, and I don't know that anybody knows, right? That's why we do research. But
Right.
um, but I would say, so I wrote this piece that appeared in Nature as a one-page sort of opinion thing.
Right.
Um, in 2023, where
Mm-hmm.
the point that I make there is as long as we're emitting, 40 plus billion tons of CO2 every year to the atmosphere, no
Mm-hmm.
form of CDR is a climate
Mm-hmm.
solution. So we really need to be at, maybe 20% of current emissions, let's say 8 billion tons of CO2 every year that we're
Mm-hmm.
putting in, where CDR starts to be something that's sensible to do. And
Mm-hmm.
part of that is because most of these techniques rely on us having renewable energy to do it, right?
Mm-hmm.
In order for it to be even carbon negative. And as long as we are still burning lots of fossil fuels, we might as well use that renewable energy to displace the use of fossil fuels, right?
Mm-hmm.
So I would say there are two things going on here. One is, how much more research we need to get to the point where we're confident that we can do this. But the other is does it even make sense to do it as long as we're still doing what we're doing? And I would say, for us as Earth and environmental scientists, we're looking at the geophysical part and maybe the environmental impact part of things. But there are many different aspects of MCDR that still needs to be figured out. There's the technology part, there's the governance, there's the financial part. Who's going to pay trillions of US dollars to do this every year? And then there's the social part. I don't know how it is in China, how acceptable it is for these ocean interventions to happen. But in the UK and the US and other European countries, people are very hesitant about anything that touches the ocean. They don't want these deployments. So we have to figure out what people are okay with. And so there's still a lot of work to be done, not just by us, but by everybody to get to a point where we figure out if this is even a solution.
Right.
Right.
Right, Chris, right. Would you have your perspective to be shared with us?
Yeah, absolutely. I think just to kind of pick on that, I agree with what David says. We don't know how long it's going to take, and now all those issues and many others that kind of have just been flagged. I think I would say that actively or passively, the ocean's going to play a role in climate change mitigation. David's highlighted how much he's already taking up 10 billion tons per year. Many of the terrestrial-based approaches, such as enhanced weathering, are looking at the oceans as a repository for that stored carbon. And even when you look at the CCS methods, certainly in Europe, all that CO2 is going to be stored in offshore reservoirs. So marine environment will play a critical role. Marine processes will play a role in our battle against climate change. I think the ultimate challenge is at what scale, and I think we have inherently in our heads, it's a blue planet, we're going to just do everything all over everywhere, and we know already that that's not the case. We can't do marine CDR in all these areas. Every approach will have its nuance, it will have a focus area. David's already highlighted the need to look at coastal oceans, which have a very different response reaction to open seas. So I think we need to sort of really turn down the dials and focus on what is going to be realistic, but also kind of recognize that the oceans will play a role in some form or other. The question is what can be done responsibly, safely, and in a sustainable, economically viable manner. We can't, at this point in time, get all these ships out to the Middle Ocean to do fertilization. Even if it was viable, we just don't have that infrastructure, we don't have the capability, it would cost too much. So I think, we need to sort of be realistic in the near term, but also recognize that the oceans have this capability. And the question is really kind of what do we as a society want to achieve in the long run? And again, I echo David's statement that, you can't there's no point doing CDR while the taps are still full, right? Whilst overflowing. So the first thing is to turn off the taps. So we have to deal with our emissions. And then at that point, look at what CDR option is going to be supportive and to what extent.
Okay, we have Yan Li. Yan Li, Dr. Lei, it's great. You want to say something? Please go ahead.
Hi, good afternoon. Hi, I'm very happy to be invited. Just now I heard David's presentation is excellent. Now I will introduce my working group. I'm co-owner and manager in the ISO International Standard Organization, and my working group name is Ocean Negative Carbon Emissions and Carbon Neutrality. And now a serious international standard is in the process of establish. The first one has been successfully approved. It's general guidelines for the ocean negative carbon emissions. And the second part will involve calculating and modeling, and in which the international standard experts will focus on MCDR, for example, or the scientific protocols and engineering approaches, calculating and monitoring and something like that. Just last week, I just come back from Yokohama, Japan, attend MCDR workshop. I'm invited speaker. And then in now this topic is very hot. The MRE now is essential because it's really needed for the ocean economic. Because do you know CBAM is European carbon boundary adjustment mechanism will start from next year, January 1st. We will pay the carbon tariff. Therefore, MRE is essentially concerned. So I will invite you experts to attend our working group, and I will want to share our draft about the second part of ISO standard, which is focused on calculating and modeling, and also included MRE some information. Because now most of my colleagues are from national standard in each national standards from different countries. Most are not scientists. I really want to search for the scientists, ocean scientists working on MCDR and MRE. So, Professor Zhang, Chuanlun, please can forward my email or my information. I will send you some material, my documents, and share to the U.S. international experts.
Okay.
So, yeah, I'm also interested. I want to know if you are interested. The expert want to join. Because if you want to cooperate this our international standard, you will also obtain the authorship in your in your country. So finally we will publish ISO standard in the ISO.
Okay.
So okay.
Right, great. Thank you, Dr. Lei, for sharing your information with us. I will connect you with Dr. Ho and Dr. Pearce about your invitation for joining the working group. I'd like to, let's see, say what's in the chat room from Maria, Kevin, VUB, for thanking for what Dave and Chris honestly discussed here. Maria, would you like to add anything to your comments?
It's just really interesting to follow this this webinar because as I was saying, a lot of the voices are coming from commercial entities who have the
Right.
financial sometimes
Yeah.
goal. So you want things to
Yeah.
work. So it's good to have a
Sure.
summary of how things are going. So thank you so much to the speakers.
Well, thank you so much, Maria. I just want to share this information collected by Yernar. This webinar has gained attention globally. We have we have a record of over 450 something registries to attend this webinar. So your voice is heard. Chris, David, thank you again for this wonderful seminar, for your participation, for your contribution. I think with that, we are into this seminar. Thank you all.
Thank you very much.
Thank you.
Bye, Chris. Bye, David. Bye, everybody.
Thank you. Bye.